Okay, so now why do people at all do this Fourier stuff? So suppose we continue with gymnastics. Now, this one was dimensionless. They're just numbers, integers. But suppose you're in a lab and you have a bench in front of you and you have inches and fractions of inches marked on that bench. So what about if you have dimensionful case? So you're an experimentalist. So in front of you, you have a meter stick with origin 1 inch, 2 inches, 3 inches, tuck, 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 n minus 1 inches, n inches total, which means you have n intervals and they can be labeled by 0 to n minus 1. And you do your measurement. For example, you have a pile of sand between two plexiglass plates. So it's something like that. And, you're shaking that, or you're studying some kind of dynamics of sand piles, let's say. So you measure this, your value, measured at every inch. So as experimentalists, what you do, you sample. And by the way, I should give credit where credit is due. This week, I'm following Stone and Goldbart, Appendix B. Both Stone and Goldbart are two extremely good physicists, but they're very nice people, so they will not be very famous outside of our community, really deep thinkers. They're both poor kids from England who had to flee the caste system of England and have found home in Urbana, Illinois, a democratic place. Same place where Phil Anderson was raised. We're doing things in inches. And the thing that's really important about this experiment is not the distance I measure, but it's really the relative distance that's important. Because what I set my inch origin is largely irrelevant, but how the thing varies is all the information about the problem. So you really care about comparing this function at two places. So you really look at when you're going to do Fourier transforms, in dimensionless way, they were written as relative distance in the number of the bin. But when you really do the measurements, you replace the number of the bin because x is now some multiple of the basic unit. This is what you really measure. It's dimensionful object. And the dual to that, the thing that shows up multiplying it depends on my roots of unity, is 2 pi over n inverse length because I stuck it in here and I had to absorb it there, so the exponent is dimensionless, times m. So this is the object that will really show up in all kinds of measurements when you take the units. Another Kronecker delta, which I used to always write as sum over pure phases, dimensionless, distance between 2 points. This Kronecker delta really only cares about the difference. So as long as the difference between the distances is 0, I get a new representation of delta, which is kind of dimensionless, but it's suitable for us taking continuum limits. What we did so far, that's called a Fourier representation of the finite set. And what I really am measuring, I'm measuring this in distance units. And now what I can do is I can represent the function by sticking identity in Kronecker delta and summing over all the components. Why do I do this? Because I can write this as e to the ik by substituting my my formula for the delta here. Formula for the unity, so that's resolution, spectral resolution of unity by Kronecker deltas. Here is the length. Here is the mth component in inverse length. And we get a coefficient here. And that coefficient has a formula which is 1 over n that came from definition of the Kronecker delta. But I take all the components of the function over entire global interval, every place where I've done the measurement, and I add them up, I average over them with this oscillating complex weight. Because this number runs on a unit circle in the complex plane. So that's a Fourier representation of your experimental data. Everything that's been done so far is algebraic identities. We took no limits, nothing. You might or might not find it useful as experimentalists to rewrite your data in this way. It turns out if your function you're studying is smooth, this is extremely useful rewriting of the theory. For future reference, let me look at a special case. If function that we are measuring, and usually that's the case unless it's some kind of electromagnetic measurement or quantum measurement, is real, then it turns out the way that it's convenient to put a meter stick is to center my inch or meter stick, put origin here, measure m inches to the right, minus m inches to the left, and look at our function there where, now this is f of 0, f of m minus 1. It's convenient to take n to be odd number, and there is a center point, and there are m points to the right and m points to the left. If you do that, then the Fourier representation takes a symmetric form. You go from minus m to m. We haven't done anything special, but now reality of the function has a very clear manifestation that you will often use in practical calculations. That if function itself is real, if I take its complex conjugate, it doesn't change. What it does in this sum, it changes minus to the plus in this phase, which you can compensate by saying that, observing that e to the minus m, you take complex, this in general complex coefficients, but now m goes to minus m is complex conjugation, and reality says that the complex conjugate of symmetrically described function is its value at minus m. Every experimentalist does his or her measurement to the best of our ability, but they use, meter sticks, imperial toes and feet and claws and whatever stupid measurement system they use. And to be able to compare them, it's very convenient to take a continuum limit if that can be done. Not all data sets lend themselves to continuum limits. And now what will happen is that, well, so far we had finite, we have finite Fourier sequences. We would like to go to the limit where we take lots of points. And now there are two possible ways of taking this limit, and both are important. So I want to make sure that we feel comfortable with them. One is called Fourier Series. If you remember, series was a limit of a sequence that is infinitely many terms. And what you do there is you imagine that you're on a periodic domain, so you can represent it as a circle, as a necklace of points. And you start your measurement with 1, 2, 3, 4. Let's say n minus 1 is 9. So 10 points in all. Then you say, aha, this is very interesting. Let me be more careful. So let me put more points. And let me even do this better. This is working really well. Let's put more and more points. So what's happening is that you have a compact support because circumference of the circle is always the same. You are measuring it. And now what happens to these compact objects, the Fourier series will turn out to be eigenmodes of perturbations of these guys. So there'll be ring tones. You hit it and various things show up. They'll wiggle around, but they have to continue wiggling. So they have to have an integer number of wiggles around the circle. So if you have a good ear, you will hear discrete ring tones whenever you hit it. You can even make experiments with a tuning kind of device where you can excite this thing in a single sharp, discrete ringtone. So you'll be able to say, this is a deep note. I have 3 wiggles around. This is a very high note because I had 27 wiggles around. But it'll be discrete. You'll be able to count. Now, the other possible limit is the one that seems natural, where you sit in a lab. It's called Fourier Transform. And what will happen is that while Fourier series will have to do with sums, Fourier transform will necessarily have to be integral. So the essential difference is that this has non-compact support. So suppose you are measuring turbulence in a pipe, and in 1825 you make a pipe that's quite short, meaning it's 10 times its diameter, and you publish your results and you prove that Stokes is wrong because his predictions are wrong. This really happened. This is a true story. And in your experiment, you put some measurements here, 0, 1, 2 millimeters, whatever. But there is a young Launis, and she doesn't believe you. So she takes much longer tube. And in much longer tube, the little steps are very small compared to features you see in a turbulence. So compared to physical phenomenon, this is getting to be very fine resolutions. And she can do it because in the third millennium, it's cheap to do calculations or observations with lots of points. And she proves that Stokes was right. The theory is absolutely wrong. What was wrong with the experiment in 1924 that killed Stokes and made Navier-Stokes equation. Navier-Stokes took another 25 years. Was a bad experiment. It was a wrong experiment. The fine experiment is in absolute agreement. Now, suppose you're a theorist, and for you, a pipe. So today, these pipes in experiments are maybe 3,000 diameters instead of 5. But your theory, as far as you're concerned, 3,000, 5,000, 10,000, they're all just fine resolutions of smooth turbulent structures in a pipe. So yours one goes off to infinity. And when that happens, you cannot distinguish two nearby frequencies. So what you get is you get continuum. In practical work, in measurements or in analysis of faces, pixelated pictures and stuff like that, images, you always do what we did last week. You always have discrete sets and you do the best jobs you can do on them. The best job could be that in a limit of finite resolution, you're getting discrete ringtones because your object that you're sitting on is still compact. Or you sit in a lab and you say, well, I can extend my pipe in both directions, arbitrarily far off to infinity. So there is a fundamental difference between compact support, in which things oscillate, but all the eigenmodes have to have integer numbers of wiggles to be continuous around the circle, and Fourier transforms as opposed to series, which are integral operations, and they assume that space is infinite from plus to minus. And, that's our assumption when we look at Euclidean or Minkowski or general relativistic spaces. We assume they're infinite for all practical purposes, of course. At Planck length, something might happen, but most of our work is not there. Take-home point. There are three kinds of Fourier analysis. One is finite set, that's discrete Fourier modes. One is compact support sets, that's called Fourier series, so infinitely many ringtones, but all of them sharp. Or Fourier transforms, in which the transformation of your function has a continuum momentum or continuum frequency and not discretized one. So now what we want to do is, we'll do it first on a circle. We want to interpolate more measurement points. So we were in centimeters, better measurement, more computers enable us to in millimeters. Then we go to Turbino ultra-fast laser lab and we measure things in microns, etc. But we always do it on a circle, or finite domain. Doesn't have to be periodic, but finite. Its length always stays the same. We're just putting more points on it. We're not making it longer. Whenever we have a sum, it's natural to multiply it by our delta x, our basic unit, lattice spacing, and take a limit, define the integral the way Euler would have defined the integral by saying, I have some density of points and I have my basic length, and let's call this thing x. So this is my best attempt at measuring a continuous length, and then the increment, I call it delta x. I'm supposed to do the usual So now I have representation of a sum, but I'm supposed to insert identity, which is Kronecker delta. To achieve what we call spectral resolution, to every eigenvalue in a spectrum associated with subspace. So what we are doing is, we used to have a function MA. We replaced it, well, we define it to be, dimension full by putting Kronecker delta here. I'm sorry. But now it's in units over A, because I added this A. And this thing goes into continuum limit to a function which, we have to write in continuum. This function has a name. It was invented by Dirac in early 30s when he formulated quantum mechanics the way you're often taught quantum mechanics in modern time. What Dirac delta is morally, but you have to be careful how you define it in various continuum settings. It's really the number of lattice points, because 1 over A is an interval. 1 over A is number of intervals in a unit volume. And that limit is called Dirac delta function. So if you're confused, you can do it numerically. So this is X space, and it has a property that it's 0 unless the argument. And now Dirac delta is worrisome thing in continuum, is divergent as 1 over A, which is the number of lattice points per unit volume. So we'll always have to be careful that Dirac delta makes sense in a limit. And the way that the mathematics how it works, and also good intuition works, mathematicians call delta distribution. So it's not a nice function the way we like to think of nice function, because something that's 0 every place and then goes to infinity at a point in this limit. But if you put it inside of an integral, then this Dirac delta function pulls out the value of integrand at its 0. So as operation, it's very well defined. And you think of it as a limit of, a peaked function whose integral is 1 and arbitrarily narrow. So that, that makes sense and it works fairly well. Still, you have to be careful. Okay, so here we have set up the thing by saying, well, the sums could be converted to integrals if I use length, dimension full length as the, sorry. Let's now do it a little bit more precisely. Take the continuum limit. In the case while length is fixed, that's the first case. I'm in my lab, experiment is 6 inches long and I'm just refining it. In that case, if I take a smaller lattice spacing, I have to increase the number of points in such a way that a product is fixed. So I'm always looking at the same measuring stick of length L, but I'm looking at a finer gauge on it. We let, in the first version of the continuum limit, you let spacing go smaller, the number of points increase, but with a constraint the fixed, and then our Fourier representation goes to an infinite series in a limit. By series, we mean there are discrete terms, but there are infinitely many of them. So Fn of A, which used to be represented by a finite number of terms, goes to a limit of a continuum variable x. Refine the thing, but I haven't moved my point x. I just changed how many steps I need of constant spacing from the origin to it. I keep it constant. So m has gone off to infinity. There is a Fourier, what we call a Fourier coefficient, a Fourier component for each m. And the factor here is 2 pi in inverse length units. Back to compute the Fourier coefficients, these guys. Then we are measuring points on a unit interval. I multiply, divide by A, f of n A, e to the pi I over L m position NA. This now goes to n times A is a length, and that we keep fixed. A goes into the definition of dx, but the sum now becomes an integral over finite interval because our rod stick is finite, fx. And now this becomes e to pi m L. So now we integrate over finite range, and we have this, curious asymmetry. When we made the Fourier transform in one direction, so going from space to Fourier components, there was a discrete sum. It was sum of all the ring tones of a circular ring. But when you do it in the other direction, this actually is definition of integral because x has become a continuous variable on a finite element. And what we are doing is we are averaging over the finite interval, my measuring stick. I'm taking the function and I'm weighing it by a phase which varies continuously with x. Now there is another way to write this that is, you might have seen it written by combining these guys in sines and cosines. So there is a term here where m is 0, that's a constant. You pull it out. And 1/2 is a correct normalization to make it consistent. And then the rest can get written in terms of two real functions with coefficients. So that if you add up terms, if you replace E by Euler formula cosine and sine, you get two terms. Now notice m now just goes positive from 1 to infinity. The 0 was taken out special. And if m is non-zero, then you actually pick up am and a minus m, because you take, e to the I and e to the minus. So this picks out symmetric part of a function because on the symmetric x going to minus x. And then there's asymmetric part which picks up I from the definition of sign. And then complex conjugation gives you the minus sign here. So this is antisymmetric. So while for me it's natural to think of Fourier analysis in terms of roots of unity, in applications when you have real numbers, real measurements, you're looking at vibrating strings, etc., then it might be natural to use cosines and sines, and that's called trigonometric representation of Fourier. And I will continue with Fourier transforms.